Dear students, today we are going to learn about subspaces. A non-empty set H, which is subset of V, is said to be a subspace. Is said to be a subspace of V. Is said to be a subspace of V if it has satisfies the following three properties. The first property is zero vector should belongs to H. Number one. Number two, you take any two vectors, u bar, v bar belongs to H. U bar plus v bar should belongs to H. That means it should be closed under addition. And the third property is you take any vector u bar in H and you take any scalar, C is any scalar. Cu bar should belongs to H. So a non-empty set is said to be a vector space, subspace, if it has satisfies three properties. Number one, zero vector is in H. Number two, the addition of two vectors should belong to H. Number three, one scalar into one vector, the product again belongs to H. If these three properties are satisfied, we can say that it is a subspace. So next, I am going to explain you one theorem, which is very useful in solving the problems. Suppose given V1, V2 are two vectors in the vector space V, let H is span of V1, V2, show that H is a subspace of V. So H has two vectors, that is V1, V2. So H is a span of V1, V2. That means what? H is the linear combination of the elements of V1, V2. That means H is of the form, the linear combination I already explained you in the previous classes. Linear combination, that means it is a linear combination of V1, V2 means it is in the form of CV1 plus DV2. H is the linear combination of V1, V2. H is of this form. We want to prove that H is a subspace. So now, to prove that it is a subspace, first what we have to do? We have to prove that 0 belongs to H. So I can write 0 as the span of V1, V2, that is 0 V1 plus 0 V2. Therefore, it is of the form of the span of V1, V2. Therefore, 0 bar belongs to H. So the first property is true. Next, let us take two vectors in H. Let U bar, comma, here W bar belongs to H. Let U bar, comma, W bar belongs to H. H is nothing but span of V1, V2. Therefore, U is of the form S1, V1 plus S2, V2. W is of the form of T1, V1 plus T2, V2. You can write C1, V1 plus C2, V2 also, D1, V1 plus D2, V2 also. This T1, T2, S1, S2 are arbitrary. It is your wish. You can write anything. X1, X2 also you can write. So let us take two vectors U bar, which is of the form S1, V1 plus S2, V2. W bar is some T1, V1 plus T2, V2. Let us add U bar plus W bar. What is the value we'll get? S1 plus T1 into V1 plus S2 plus T2 into V2. So S1 is a scalar, T1 is a scalar, S1 plus T1 is again a scalar, S2 is a scalar, T2 is a scalar, S2 plus T2 is a scalar. So it is again a linear combination of V1, V2. So this is nothing but it is a linear combination of V1, V2. So this belongs to span of V1, V2. Therefore, it belongs to H. So for every U bar, comma, W bar belongs to H. U bar plus W bar, that is again a linear combination of V1, V2. That is again belongs to H. Therefore, H is closed under vector addition. Next, take one scalar C, take a vector U bar, multiply it, C into U bar. U bar is S1 V1 plus S2 V2. Therefore, it is CS1 into V1 plus CS2 into V1. C is a scalar, S1 is a scalar, CS1 is a scalar. C is a scalar, S2 is a scalar, CS2 is a scalar. It is again a linear combination of V1, V2. Therefore, C into U bar, it is again CS1 into V1 plus CS2 into V2. It is a linear combination of V1, V2. So it is again belongs to H. Therefore, scalar multiplication is closed. So scalar multiplication is closed. Vector addition is closed. 0 bar belongs to H. Just now I have explained what is the subspace. So these are the three conditions for subspace. If these three are satisfied, therefore H is a subspace of V. So span of V1, V2 is a subspace of V. Next, let us take an example. Let H be the set of all vectors of the form A minus 3B. I am writing it as a vector form B minus A, B. So this is given your H. Your H is of the set of all vectors of the form. This can be written as A into 1, 0, 1, 0 plus B into minus 3, 1, 0, 1. Therefore, your H is the linear combination of V1, V2, where V1 is 1, 0, 1, 0 and your V2 is minus 3, 1, 0, 1. So just now I have explained you that linear combination of V1, V2 is a subspace of V. Here V is R power 4 because 4 vectors are there. Therefore, the given H is a subspace of R power 4. Why? Because H is the linear combination of V1, V2. That is nothing but span of V1, V2. The span of V1, V2 is a subspace. Therefore, H is a subspace. Now, one more example. Let us take W. W is S plus 3T, S minus T, 2S minus T, 4T. So, take S here. 1, 1, 2, 0. Take T. 3, minus 1, minus 1, 4. So, again, W is a linear combination of V1, V2. What is V1 here? Tell me. V1 is 1, 1, 2, 0. And what is V2 here? 3, minus 1, minus 1, 4. So this is linear combination of V1, V2. That is nothing but span of V1, V2. So W is a span of V1, V2. We know that by the previous theorem, W is a subspace of how many vectors here? R, 4. So subspace of R power 4. So let us take one more example. In the subspace, let us take one more example. W is equal to, we'll take one more example, minus A plus 1, A minus 6B, 2B plus A. So he is asking that W is a subspace of R cube R naught. Here, 0 bar, that is 0, 0, 0. See, this is equal to minus A. So 0, 0, 0, 0. Here 1 is there. If I write A0, B0, all becomes 0, but here 1 is left over here. So 0, 0, 0 does not belongs to 0, 0, 0 does not belongs to W. So 0 bar vector does not belongs to W. Therefore, W is not a subspace. Why? Because what is the first condition for subspace? 0 vector should be in W. So here 1 is there. If I put A0, B0 also, so here you will get 1, 0, 0, 0. You can't make it 0. This one. So 0 bar, 0 vector does not belongs to W. Therefore, W is not a subspace. So to prove that it is a subspace, you have to prove three conditions. One is 0 bar belongs to W. Two vectors U bar plus V bar belongs to W and CU bar belongs to W. These three conditions are satisfied. W is a subspace. Or you can write W is the linear combination of two vectors V1 and V2. That is linear span of V1 and V2. Then also we can say that W is a subspace. Okay, next. We'll prove one more theorem. Next one. Let H and K. Next theorem. Let H and K are two subspaces of V. Two subspaces of V. Then H intersection K is also a subspace of V. We'll prove how it is true. So given that H and K are two subspaces. So given that H and K are subspaces of V. That means 0 bar belongs to H, 0 bar belongs to K. That means 0 bar belongs to H intersection K. So 0 vector is in H intersection K. First condition is true. Let U bar, comma V bar belongs to H intersection K. That means U bar, V bar belongs to H and U bar, V bar belongs to K. Because U bar, V bar belongs to H intersection K, U bar, V bar belongs to H, U bar, V bar belongs to K. That means since H is a subspace, U bar plus V bar belongs to H and U bar plus V bar belongs to K. Why? Because H is a subspace, addition is closed. Therefore, from these two, combining these two, we can say that U bar plus V bar belongs to H intersection K. So if you take two vectors in H intersection K, the addition is also in H intersection K. Like that, let us take a scalar C belongs to R. U bar belongs to H intersection K. That means U bar belongs to H and U bar belongs to K. Since U and K are subspaces, since U and K are subspaces, for every C belongs to R, U bar belongs to capital U, CU bar belongs to U, and your CK bar belongs to, CU bar belongs to U, and CU bar belongs to K. Why? Because U bar belongs to H intersection K. So H and K, sorry. U bar belongs to H and U bar belongs to K. So since H is a subspace, Cu bar belongs to U. Since K is a subspace, Cu bar belongs to K. Therefore, Cu bar belongs to H intersection K. So, to prove that H intersection K is a subspace, first I proved that 0 bar belongs to H intersection K. Number 1 point. Number 2, I proved that U bar plus V bar belongs to H intersection K. Number 3rd point, Cu bar belongs to H intersection K. These three properties are satisfied, then H intersection K is a subspace. So addition is closed and you take any scalar, any vector in the H intersection K, because H and K are subspaces, Cu bar belongs to U and Cu bar belongs to K. So Cu bar belongs to H intersection K. These three properties are satisfied. Therefore, H intersection K is a subspace of V. So intersection of two subspaces is a subspace. Next, we are going to prove one more theorem, important theorem. If H and K are two subspaces of V, then H plus K is also a subspace of V. So what is H plus K? H plus K contains of the elements of the form. It is of the form. H plus K is of the form. Proof. So let us take H and K are two subspaces of V. You can write 0 bar as 0 bar plus 0 bar. 0 bar belongs to H. and 0 bar belongs to K. Therefore, 0 bar belongs to H plus K. So, 0 vector is in H plus K. Let us take two elements in H plus K. Let us take U bar in H plus K. Let us take V bar in H plus K. So, U bar is in H plus K means it is of the form H1 plus K1. V bar is in H plus K means it is of the form H2 plus K2, where H1, H2 belongs to H and K1, K2 belongs to capital K. Next, U bar plus V bar, that is H1 plus K1 plus H2 plus K2, that is H1 plus H2 plus K1 plus K2. So H1 is in H, H2 is in H, H1 plus H2 belongs to H. K1 is in H, K2 is in H, K1 plus K2 belongs to K. Because they are all subspaces, they are all closed under addition. Therefore, U bar plus V bar belongs to H plus K. Next, what is the another one? You take any scalar, C belongs to R, Cu bar. What is U bar here? H1 plus K1. So C into H1 plus K1. That is CH1 plus CK1. So C is a scalar, H1 belongs to H, CH1 belongs to H. Why? Because H is a subspace. C belongs to R, K1 belongs to K, CK1 belongs to K. So CH1 belongs to H, CK1 belongs to K. Why? Because it's a subspace, it is closed under scalar multiplication. Therefore, Cu bar belongs to H plus K. So three conditions are true. One is 0 bar belongs to H plus K. Addition of two vectors belongs to H plus K. The third one is scalar multiplication is closed under H plus K. Therefore, H plus K is a subspace of V. So addition of two subspace is a subspace. Intersection of two subspaces is a subspace. And if any problem they have given, write it as a linear span of the vectors. If it is able to write down as a linear span of the vectors, we can say that it is a vector space. When any problem is given, ask you to prove that it is a subspace. What you have to do, you have to write as a linear span of the vectors. If you are able to write as a linear span of the vectors, then it is a subspace. Otherwise, it is not a subspace. For example, we'll take one more problem. W is equal to S plus, write one more. W is equal to 5B plus 2C, BC. So take B common, write as 5, 1, 0. Take it as C common, 2, 0, 1. So W is a linear combination of V1, V2. V1 is 5, 1, 0. V2 is 2, 0, 1. Therefore, W belongs to linear span of V1, V2. Therefore, W is a subspace. So these are the methods to do the problems in the subspace. The three theorems. What is the three theorems? One is linear span is a subspace. The intersection of two subspace is a subspace. The addition of two subspace is a subspace. So the three theorems. Learn the three theorems and these type of problems in the subspaces. Thank you.